Hello, chemists. This is Ms. Placino, and you're watching lesson 11.1 on factors affecting rate. In today's lesson, we're going to talk about how we can change the rate, or the speed, at which a chemical reaction occurs. Goals for today's lesson. You should be able to explain what the collision theory is and how it affects reactions. You should also be able to identify the factors that affect the rate of a chemical reaction and explain how those factors are impacting the rate. Those last two are the big ones for today. Let's get started. In this lesson and lesson 11.2, we're going to be looking at chemical kinetics, which is really just a branch of chemistry that is concerned with the rate, again, just the speed at which chemical reactions occur. We're going to be focusing on the basics today and really building in 11.2. So let's think about this. What must happen between reactant molecules in order for a reaction to occur? Regardless of what type of reaction is occurring, we need our reactant molecules to collide. If the reactant molecules never come in contact with one another, they never have a chance to react and form the product. So according to collision theory, there are two different types of collisions. We can have effective collisions, which, as you might imagine, these are the type of collisions that produce the desired product, so basically the thing we're trying to make. And we can have ineffective collisions. These are collisions that will not produce the desired product. Sometimes an ineffective collision is no reaction whatsoever, or sometimes you end up producing a product you didn't want. That might be kind of weird to think about at this level of chemistry, but as we get to larger, more complicated molecules, it's not uncommon for them to be able to undergo a number of different reactions. So that's what we mean when we say not the desired product. Let's look at this in terms of pictures. So here's our effective collision. We've got our reactants, chlorine atom and this molecule containing chlorine, nitrogen, and oxygen. They collide, and then after the collision, we end up producing Cl2 and NO. Let's compare that to an ineffective collision with the same reactants, same molecules. The collision occurs, but after the reaction, nothing has changed. Let's see what could have caused this to occur. What are some differences you notice in the before collision picture for both effective and ineffective? Yeah, maybe it jumps out at you that they have different orientations. So effective collisions need to have correct orientation. And in an ineffective collision, you of course have incorrect orientation. What other factor might be playing a role here? It is definitely difficult to tell from the pictures. But speed is going to play a factor as well. We need the molecules to hit with enough energy to get new bonds to form and old bonds to break. I would argue in this ineffective collision, since we don't see any reaction, in addition to having the incorrect orientation, we also see insufficient speed. So speed is really just related to how much energy the particles have. Orientation is something we can't control. It's got all those particles moving around very randomly, and you cannot really kind of line up the reactant molecules and smash them into each other at the correct orientation and speed. It just is going to be kind of just statistics and the odds of them bumping into each other in the correct orientation. Let's try to relate this to potential energy diagrams. Okay, so we've got these two different diagrams. Hopefully the one on the right looks very familiar. That is our potential energy diagram. The one on the left is showing a relationship between kinetic energy and then the number of particles with that kinetic energy. So you don't have, like if the temperature of a substance is 50 degrees Celsius, not every single particle is at 50 degrees Celsius. You've got this distribution. This dotted line with the arrow, that represents our activation energy. So if we go over to our potential energy diagram, hopefully you remember that the activation energy is represented by this arrow. It's the amount of energy required to start the reaction, to really go from the reactants up to the top of the hill, which is the transition state. This means that the reactant molecules have enough energy to react. So they have enough energy to collide and potentially get a reaction of some sort to occur. You'll notice that only a small fraction, in this case, of the molecules have enough energy to react. The vast majority of them aren't moving fast enough. They don't have enough energy to react. So when they collide, they won't hit with enough force to get all the way up that hill. Only the ones in this blue section of the graph have enough energy to get all the way up the hill, have that effective collision, and then go on to form products. What we're really going to look at today is different factors that we can control to try to speed up or slow down a reaction. And we know reactions occur when effective collisions occur. So we've got things like speed, orientation, and frequency of collisions. It turns out we cannot control orientation. Again, you can't hold the molecules in positions to smash them together. Speed is really related to temperature. And the frequency of collisions, this is what we're going to try to manipulate. The more frequently molecules collide, the greater the odds are that they'll have enough speed and the correct orientation to react. The less frequently reactant molecules collide, well, then there are less chances for that reaction to occur. So we're going to focus on 6 different factors that we can use to try to control or impact the rate of a chemical reaction. Ultimately, most of them are going to focus on, how frequently collisions occur or just simply the number of collisions that occur. We're going to do this Pictionary style. So I'm going to show you a picture. You're going to try to tell me what factor I am, trying to hint at with that clue. All right, let's check these out. Okay, our first picture. What am I trying to show you here? What factor that affects rate? Hopefully you're thinking this is the relationship between temperature and rate. We just spoke about this briefly, but as temperature increases, reaction rate increases as well. Think about what's happening to the particles. As you increase the temperature, you get particles moving around faster and more randomly. So that's going to increase both the frequency, because they're moving around more randomly, and the effectiveness, they're moving faster, of a reaction. So we have more frequent and more effective collisions. Temperature is the only way to make the collisions more effective. None of the other factors that we talk about can make particles collide with greater speeds. So definitely make note of that in your notes. This occurs because as temperature is increased, as we go from T1 up to T2, going from that red, bluish curve to the red one, activation energy is going to stay the same for a reaction. You can see that now at higher temperatures, more of those reactant molecules have enough energy to react. If you look at the blue one, fewer of those molecules have enough energy to react. That's why we tend to see slower reactions at colder temperatures. I guess this one I've kind of spelled out for you. What are we trying to show here? This is pressure and rate. Which one do you think leads to a faster reaction rate? Lower pressure or higher pressure? As pressure increases, we tend to see increases in reaction rate as well. Why? Think about collisions. At higher pressures, you've kind of forced all those particles closer together, so you're just going to see more frequent collisions. They might not be any more effective, but they'll be colliding more often. Just to kind of put some numbers to it, maybe instead of colliding once every 10 seconds, they're colliding 5 times every 10 seconds at a higher pressure. So just because there are more collisions, you have a better chance of those collisions being effective. Please make note. This applies to gases only. Solids, liquids, and aqueous solutions are really unaffected by changes in pressure. Gases, on the other hand, are extremely sensitive to changes in pressure. So you can only change the rate of a reaction if your reactants contain at least one gas. All right, number 3. What am I trying to show you here? This is surface area and reaction rate. You might have some experience with this, like a sugar cube versus granulated sugar dissolving into something like coffee or tea. Yeah, as you increase the surface area, reaction rate tends to increase. So this cube has low surface area. When it's broken apart into smaller pieces, it has high surface area. Only the particles that are just like in contact with the other material, like if you're thinking about dissolving, so the part on the, like the sugar cubes, we'll just use that as an example. The sugar molecules that are on the outside are going to be able to react with the coffee. The stuff that's in the middle isn't in contact with the other reactant, so it can't dissolve. So as I increase the surface area by cutting something up into smaller pieces or grinding it up so it's a fine powder, I should really just see more frequent collisions because more particles are exposed. What phase of matter am I going to be able to change the surface area of? Hopefully you're thinking solids. Gases, liquids, and aqueous solutions, you can't change the surface area of, at least not in any meaningful way. So it's really just solids only. Clue 4, what are we doing here? This is concentration and rate. So over on the left, we have a high concentration. Over on the right, we have a lower concentration. Which one should lead to a faster reaction rate? Yeah, the one with a high concentration. As concentration increases, you tend to see an increase in reaction rate. Why? Hopefully you're seeing a pattern. This idea of more frequent collisions. There's just more opportunities for reactant molecules to bump into one another at higher concentrations. What phases of matter are affected by changes in concentration? We're going to be looking at solutions and gases only. These are two substances that we can express the concentration in terms of molarity. Solids and liquids are pure substances, so they're always going to be 100% of that substance, so you can't really change their concentration. Gases, also pure substances, but they're really, their concentration can change based on things like volume and pressure, so we're able to change their concentration as well. This one I think is a little bit trickier to figure out. We've got a reaction between magnesium. We've lit it on fire. So it's going to be reacting with the molecules in the atmosphere. The red ones are oxygen. The blue ones are nitrogen. And our final product is this like white powdery substance, which is magnesium oxide. Any thoughts here on what we're trying to, what factor we're looking at? This is the nature of the reactants. There is more nitrogen present in the atmosphere than there is oxygen, but magnesium preferentially reacts with the oxygen to form magnesium oxide in this case. Why might that be? If you're stuck, draw a Lewis structure for O2 and N2. Which bond do you think is going to be easier to break? That double bond between oxygen atoms or that triple bond between nitrogen? Yeah, you can kind of imagine like trying to karate chop through boards. Molecules with weaker bonds react faster, or in this case, they're going to kind of react preferentially. It is easier, or it requires less energy, to break the double bond that exists between the oxygen atoms than it is to break the triple bond that exists between the nitrogen atoms. That's why we see magnesium oxide getting produced as the major product and not magnesium nitride. Make a note, aqueous ionic compounds are going to react the fastest. If you think about double replacement reactions, which we talked about last semester, almost as soon as you mix those two aqueous solutions together, you get a reaction. Why is that? Think about what happens when you take an ionic compound, maybe something like sodium chloride, and you dissolve it in water. What does it do? Oh, it breaks apart into ions. Both be aqueous. In an aqueous ionic solution, you have already broken that bond. If you think about your potential energy diagram, breaking the bond is the most energy-intensive step of the whole process. So by dissolving an ionic compound in water, you've already broken that bond, and now you just have these ions floating around in solution that are going to react immediately upon contact with another ion. So if I try to mix sodium chloride with something like silver nitrate, for example, I'm going to create a white solid almost immediately upon combining those two solutions, and that white solid will be silver chloride. Definitely make a note of that. All right, our last factor affecting rate. What are we trying to show here? Might have talked about this in bio last year. This has to do with catalysts and rate of a reaction. So we're back to our potential energy diagram over here on the left. The red line is the uncatalyzed reaction. The green line is the catalyzed reaction. What changes about those two? Hopefully you notice that there's a decrease in activation energy. So a catalyst is going to speed up the rate of a reaction, really by providing an alternative pathway with a lower activation energy. Doesn't follow exactly the same path, but we end up with the same energy of the reactants and the products. So our delta H doesn't change, just the energy of the transition state and the activation energy. If we look at kind of that same diagram that we saw earlier, when the reaction is catalyzed, we've got more particles that are going to have sufficient energy to kind of make it up that hill than when the reaction is uncatalyzed. So that wraps up our 6 different factors affecting rate. We can use temperature, pressure, surface area, concentration, nature of the reactants, and catalysts to impact the rate of a reaction. Let's look at a practice problem and try to put these different concepts to work. I want to take a look at question number 3. It's asking us to provide 3 ways to speed up this reaction between oxygen and nitrogen that produces nitrogen dioxide, and we're told we cannot use a catalyst. So pause the video, see if you can come up with 3 ways and provide explanations as to why those changes will make the reaction occur faster. My guess is one of the first things that came to mind for people is to increase the temperature. We know that by doing that, we'll have more frequent and more effective collisions. Those reactant molecules are going to be moving faster, so more of them will have enough energy to react, so more of them can have effective collisions. And because they're moving faster, they're going to be moving more randomly, which is going to lead to more frequent collisions. Another way to increase the rate of this reaction, because they're gases, is to increase the pressure. This is going to lead to more frequent collisions. As you push those oxygen and nitrogen molecules closer and closer together, they're more likely to run into each other. So more frequent collisions leads to a faster reaction rate. What's the last way that I can get this reaction to occur more quickly without catalyzing it? I can increase the concentration. Just like by increasing the pressure, that's going to lead to more frequent collisions. If you've got more oxygen and nitrogen molecules in the same space, they're more likely to collide with one another, so that should also increase the rate of the reaction. Definitely practice with these concepts. Make sure you feel comfortable with how changing those 6 factors will change the rate of a reaction, and definitely play around with these practice problems to make sure that you've got the concepts down. Thank you for tuning in, and I hope you found this helpful.